Okay, I think it's time that we took a crack at some of these example problems. So let's go and take a look at one of them. My problem says that you are titrating, and I'll erase this too. You are titrating 50 milliliters of 0.1 molar acetic acid with 0.12 molar KOH, potassium hydroxide. So, the question asks, what is the pH before any KOH has been added? All right, let's start by writing down the information that the question gives us. So you have 50 milliliters of 0.10 molar This is acetic acid. Acetic acid is found in common table vinegar. It also gives you the Ka of acetic acid. Once again, if you're unfamiliar with acid-base properties and acid-base concepts, I highly recommend that you go review the rest of them too. The Ka is given to be 1.8 times 10 to the negative 5. All right, and you're given that the concentration of KOH, potassium hydroxide, is 12 molar. Okay, so the first part of the question asks, what is the pH before KOH has been added? Well, that basically allows us to do a weak acid dissociation table on your acetic acid. So let me write out the dissociation equation. HC2H3O2 plus H2O, double arrow, C2H3O2 minus plus H3O plus. I am not very good at putting my states, but you should definitely put your states in. So that's like the aqueous, liquid, and other aqueous states. You are given an initial concentration, and you want to find the pH, meaning that your most likely approach is going to be an equilibrium table or an ice table. So let's set that up. Your starting concentration is 0.10 molar, and we ignore water. Why? Because water is a liquid, and in solution, liquids and solids basically have massive concentrations. So we don't look at the concentration of water, and if you knew what the K expression is from earlier on in the unit, you would also know why we don't consider H2O. Okay, so we have this. This is our equilibrium table. So we don't know how much this dissociates. So we have minus X, and we start off with 0 acetate, which is the conjugate base, and 0 hydronium. But now we would have to write our dissociation constant, acid dissociation constant. So X squared, or X times X, over 0.10 minus X is equal to that dissociation constant. Typically, to solve this problem, you would actually need to multiply everything out, which results in a pretty ugly quadratic formula problem. But if we look at this value, we actually see that that value is really small. And after doing it through multiplying, if we ignore this x, if we assume this x is too small and too negligible, we actually get an error within 5%. And that's called the 5% rule in AP chemistry. I'd recommend too that you read more about that if you're unfamiliar. So we can ignore this x, and we will have this times 0.1. So your x squared is equal to 1.8 times 10 to the negative 5. Let me very quickly fetch my calculator so that we can work through this. Hold up. So we had this equal to x squared. Now we just take the square root and find x. Well, what is x? So my x, I get around 1.34 times 10 to the negative 3. What is x though? X is the concentration at equilibrium of acetate and of hydronium. But since this question asked us to find the pH, we simply treat this as our hydronium concentration. And pH, once again, is found negative log of this value of hydronium ion concentration. So I get a pH of 2.87. All right, that's the easy part of this question. What if the question does ask you to add KOH? And what if it asks you, how much KOH do you need? Well, to find equivalence point, remember your moles of acid that you start off with and the moles of base that you end up with